Hello everyone, my name is José Almeida. I'm a researcher at CHECAD in the Polytechnical Porto, Portugal, and I'll be presenting the paper titled Intraday Energy Resource Scheduling for Load Aggregators, Considering Local Markets. I have here a small agenda of what this presentation will consist of. First, I'll start with a small introduction, then I'll present the proposed methodology consisting of the intraday model and the mathematical formulations. Then I'll talk about our case study with our 13-bus distribution network and forecasted technologies. Then I'll be presenting the results, and finally I'll give some conclusions and future work. So, for the introduction, our main motivation was to provide new models so that the distribution networks can cope with high demand and the distribution energy resources, in this case, energy storage systems. The proposed model intends to simulate the future of the distribution networks, where multiple aggregators and/or electricity suppliers will coexist in the competitive environment, um, creating multiple opportunities for all the entities involved, because these aggregators or electricity suppliers will try to provide the best product for the end user. So, for our methodology, consisting of the intraday model, we propose a model that optimizes energy resource scheduling for the hour ahead, consisting of four 15-minute periods. So, for our intraday model, we first need our technical data consisting of the external supplier and our dispatchable distributed generation. This is the controllable distributed generation. Then we have the load and demand response contracts. We have the wholesale electricity market, the local electricity market, and our energy storage systems. We also need our forecasted data for the uncertain resources, in this case, the load demand of the different loads, and the local electricity market prices. We also need the day-ahead scheduling results, in this case the external supplier contracts made in the day ahead and the day-ahead wholesale electricity market prices will enter our hour-ahead scheduling. Then we also need the solution from the previous hour. In this case, we need the state of charge of the energy storage systems that will enter the hour that we are optimizing as the initial state of charge of the batteries. So, for our mathematical formulation, we have our objective function, that is to minimize the costs in each hour. First, we have the operational costs that consist of the distributed generation costs. Then we have the external supplier costs. We have the energy storage system discharging costs, the curtailment costs. This is the demand response reduction costs. And we also have the imbalance for the energy not supplied, in this case for the loads. We also have here the income, which is mainly given from transactions made in the wholesale and local electricity market prices. Then we have the constraints to our problem, that is the active power balance constraint, the dispatchable generation and external supplier limits. Then we have, in the energy storage systems, we have the battery balance constraint, we have the maximum charge and discharge limits, the minimum energy stored, the maximum battery capacity limit. Then we have, when it comes to the demand, we have the demand response maximum limit to reduce the load. Then we have the electricity markets offer and buy limits. This includes the wholesale and the local electricity market, both markets. For a case study, we present a 13-bus distribution network located at the BiSite laboratory in the University of Salamanca. We can see from the figure that this network has a substation, in this case of 30 megavolt ampere. It has different types of loads. It also has renewable generation and electric vehicles, which were not considered in this case. We then define the three different aggregators based on the loads. First, we have the first aggregator, which consists of the hospital, fire station, and shopping mall. We have a second aggregator, which consists of only the residential buildings. And then we have a final aggregator, which consists of the office buildings. When it comes to our forecasted technologies, we can see here on the first case we have consider the prices for our model. The external supplier and wholesale market prices are fixed because they were closed in the day ahead, the scheduling. But then we have the local electricity market prices, which vary between these two limits, as you can see here. Then we have our total demand from the three different aggregators, and as you can see, the third aggregator has the highest values between the three. We also consider two energy storage systems, and we based on our demand response model on the direct load control with a reduction of 30% of the load for each aggregator. So when it comes to the results, we incorporated the hybrid adaptive differential evolution with decay function method heuristic for the hour-ahead optimization. We simulated a total of 5 runs for each aggregator. And as you can see from the results that we have the average cost and standard deviation cost for the day-ahead and intraday models, we can see here that the second aggregator had the smaller increase from the day ahead and presented the best results because we do not want a large variation between the day ahead and intraday model, because we want to see that our day ahead scheduling was well made. So when it comes to the scheduling of the resources, we have here the scheduling for the first aggregator. This scheduling is presented for the second hour of the optimization that obtained an objective function value of 10.81 monetary units. As you can see from the graphs, the energy bought in the day-ahead market was more than enough to satisfy the demand, because as you can see from the power consumption, the aggregator needed to sell this energy in the local market to satisfy the active power balance constraint. So when it comes to the aggregator 2, we present the fourth hour of optimization with an objective function value of 24.40 monetary units. Here, in contrary to the previous case, we can see that in periods 1 and 3, the aggregator needed to buy in the local electricity market energy to satisfy the demand. In the final aggregator, we present the sixth hour of optimization with an objective function value of 172.03 monetary units. Here we can see that the power generation on the left is given mostly from the contracted energy from the external supplier in the day ahead scheduling. And we can see also that the power consumption was mostly given as well for the sales in the wholesale market made in the day ahead. Still, there is an excess of energy, mostly in periods 1, 3, and 4, that the aggregator needs to sell in the local electricity market to satisfy the active power balance constraint. So, for our final conclusions, the proposed intraday energy resource scheduling model, we can say that obtained good results. The integration of local electricity market transactions to meet the power balance constraint was met. The second and third aggregators showed a decrease in the objective function values, which from previous cases is not expected to occur, but note that we used an heuristic for the optimization, which does not guarantee an optimal solution, and we considered as well the local electricity market 25% more expensive than the wholesale market, which can change the results according to the local electricity market prices. So for current work, we incorporated more aggregators, creating a more competitive environment in the network. We are also applying a risk-based methodology to the scenarios to give us a better and safer solution. And for future work, we need to validate our solutions with the distribution system operator. Yes. So thank you. Thank you.